Here we're going to go through some things we need to be careful of. When doing all of this linear regression, we have these conditions we should meet. And the condition that we talked about already is that our scatter plot should be roughly linear, but there's other conditions that we should think about as well. First thing we should always think about are these lurking variables, which we talked about before as where we need to be careful that we don't mention cause and effect, that one thing is causing another, even if we see a trend, because just because we can graph two variables together doesn't mean that they're related to each other. There might be some relation, but there might be a missing link between them. So we have in this graph here is a map of different countries, and what they did is they took how many TVs there were per 1,000 people, and they also graphed their life expectancy. So the idea being, like, here's the United States. People in the United States, a lot of us have TVs, and we also have a fairly high life expectancy. Whereas down here with Angola, as you can see, barely any TVs there, a very low life expectancy. However, where we get this moderate strength and this kind of pretty linear trend here, we wouldn't want to start talking about, well, as you increase TVs, it increases life expectancy. Like essentially saying, if you own more TVs, you live longer, and it's just not true. You can't go to Best Buy and buy 100 TVs and then you'll live forever. That would be nice if it was that simple, but it's not. The idea is that there's something else connecting. So if we think about some possible lurking variables, it's that countries that have more TVs just tend to be more developed. With that, there's more technology available, and if there's more technology, then that's probably filtering into the healthcare system. There's probably more machines available, more tests available. And with that, that'll increase life expectancy. So some lurking variables are that it kind of deals with the development of the country. And with that comes kind of the level of healthcare available and technology. We have these different lurking variables that are actually connecting the two. It's not just about TVs and life expectancy. So we want to be careful of these lurking variables that are actually creating this kind of stronger, in this case, moderate strength, and not just directly relating the two variables. So be careful of those. Something else we want to check out are the residual plots. So where we check that the scatter plot is roughly linear, which in terms of these scatter plots we see down here, we can see this one is very nice and linear. This one is somewhat linear, but what you can notice is a little curvature to it. And when we have that curvature, that's what we want to be careful of. But maybe in our scatter plot it's not that obvious. And same thing with this, where we can kind of see this linear trend. What we might see is a scatter plot that looks okay, but when we go to a residual plot, what the residual plot's graphing are these residuals that are occurring. So you keep the same x-axis, that's what the coordinate is saying here. So we're working with the same x-axis across the two graphs, but then what we're graphing is a little different. What we're graphing is the difference between that observed value minus the predicted value. So like if we look at this little point right here, it's that it's landing pretty much on the line, and we see that happening here. It's because the distance, we have this middle line on our residual plots, this is where we'd have a distance of 0, and then we end up with more positive distances and then negative distances. So the further we get away, the higher or lower our points are going to be. So what we want to notice with these residual plots, in our case of this very nice linear plot, we end up with this nice scatter here. And what we should be seeing with these scatter plots, and in the original scatter plot, what we want is most of the points close by the line. Maybe we have a few that get away from it, but mostly really close by. So when we look at the residual plot, we kind of want to see the same thing but horizontally. Most of the points close by this middle, but a few points away is okay. Something that happens with that trend that I'm describing is similar to the bell-shaped curve, in that if I just flip this around for a second, this idea of, okay, not many points out here, maybe a few, maybe a lot here, and that's what we want. We want a lot in that middle, and then as we move away from that middle, less, and then we don't want any. And what that describes is a bell-shaped curve. In terms of frequency, looking across this line here, we want none, and then more and more and more towards the middle, and then decrease out to less. So we want to see this kind of normal distribution across this residual plot, where most of the points are in the middle, and then less as you get further away. Where we see this slight curvature in the scatter plot over here, it becomes more obvious when we look at the residual plot. It becomes much clearer that it's curved. So having a curve in the residual plot makes obvious a curve in the scatter plot itself. But maybe we don't see it in the scatter plot, but when we see it in the residual plot, that'll be clear that we're failing the conditions. We shouldn't run linear regression when we have a residual plot like this. And this isn't matching the idea of a bell-shaped curve. It's kind of like, okay, absolutely none. Then we have a lot, and then, yeah, it becomes kind of skewed in a way. And with that, we don't want to see that. Then with this last case, where we have so much scatter, and even though we can roughly see a line going through, I mean, this is a case of a very weak correlation. And when we have a weak correlation like this, if we look at the residual plot, it's kind of like, it wouldn't make a normal curve, it would make a uniform curve, where everything's kind of equally occurring. It all has kind of a same frequency. So you'd have a graph that would kind of look like this in terms of frequency, and we don't want that. So when we have these weak correlations, we don't really want to talk about R. We don't want to use, or especially this equation of the line, where we have this equation of the line, that's not the best prediction really. If it's so weak, it's not predicting things accurately if things are scattering all over the place. So often what we do is when we have a weak correlation like this and we're trying to make predictions, all we do is use the means. Use that mean of y that should be coming through. And that's what we found in the technology, is it gives us the means. And if we're trying to make predictions with this model, just use the means, because this line isn't a best prediction, since there's just not really any correlation. So something we want to do is look at these residual plots, which we can use technology to give us these residual plots by going to where we see the drop-down menu that says scatter plot. Click scatter plot and switch over to residual plot. Then it'll just give you that residual plot. There's our 0, and then you get an idea of the distances. We can see Miami there with that big residual. But we're getting that idea of, okay, most of the points are close by, then some are far out there, some out there. But this idea of less and less, okay, a few, the most of them, and then it decreases out from there. So you can use GeoGebra by switching between scatter plot to residual plot to double check that there isn't any obvious curvature, also checking that it's not just scattered all over the place. This will give you a better idea of, is our scatter plot really linear? So, checking this residual plot, make sure there aren't any bends. Be careful of any outliers. They're going to be clearer when we get to the residual plot. And then make sure there isn't any change in spread. What this can kind of look like, I always call it the tornado, because it just kind of looks like everything's close. And then the scatter plot's like things get further and further away. And you can see that occur in the residual plot as well. It kind of switches over where you have that middle line, everything's close by, and then things become more and more scattered. That is another part where we don't really want to use linear regression. or especially this equation of the line, because it's not actually a best predictor when we end up with so much variability out here at the end. So just be careful of those three things coming through. And then when you have a scatter plot and you make your residual plot, what you kind of want to visualize here and kind of separate it like this. If we made a histogram of frequencies, it's like in here we have 3 points, here we have 5, here we have 4, there we have 3. The idea being that it's low and then it increases to the most, has the most, and then decreases out. That's the kind of distribution of these residuals that we want to see in there. So our conditions to check: make sure the scatter plot appears linear, and just to confirm it is linear, double check that residual plot and make sure it's looking fairly normally distributed around that line of 0. And then also just be careful of those lurking variables.